Hello, you beautiful people out there. Today I want to show you a chemical reaction engineering view on the coronavirus. So when I prepared the last lecture, we talked about the autocatalytic reaction and about the Euler scheme. And now I want to show you how we could use this to have a little look on the coronavirus. So first, I want to show you what are my data sources. Then, how can you model something like the coronavirus if you just assume it could also be a chemical reaction. And yes, basically it's something close to the autocatalytic reaction from the previous lecture. And again, for the results, we will use the Euler scheme. So, first a note. I'm not a physician, so basically I have not any clue about medicine and so on, and I'm just playing around here with chemical reaction, and this is not a proper prediction of the future, but I just found it interesting for me. That's why I want to show you how you can use chemical reaction engineering also for this topic. Okay, let's start with the data. So I use it's called Worldometer. There you find tons of data and graphs, and you can choose between a linear scale and a logarithmic scale. And so for me this is very interesting. You find daily updated figures for the total cases and new cases and so on. Then especially for Germany, I take the data from the, I think it's Berliner Morgenpost, yeah, it's written there. There you can see how the figures for Germany evolved. So basically they are all coming from the Robert Koch Institute, but I like this graphic here a lot. And the actual data for each day I take from Wikipedia. They are also from the Robert Koch Institute, RKI, and here you can see this. Okay, so I just copied the cases for Germany and plotted them again. And so to use the regression function of Excel, it's more convenient to not do it with real data on the x-axis, but just with days, and here on the y-axis you have the cases. So day 4, so I skipped all the data where statistics is not really properly, it's not really correct. So I said, okay, I start here at, this is day 4, and this was the 24th of February this year. And then you can put it as a nice regression exponential function, and the r squared is quite good. So then it's more convenient to put it like a semi-logarithmic plot. Here you can see that you have in this region that you have quite clear exponential growth of this. So to have a better statistics, I only used the blue dots here. So these I omitted because here you have only very little cases, so it's not very good for the statistics. And yes, I used this, and here this was the prediction, and these are some preliminary values, so it's quite okay. So the first day, so this was day 14, was the 5th of March, and there we had 400 defections, for example, and then it continued like this. And if you have a look at this, this is an exponential function, but you can convert it to something like it means 1.266 up to the power of x. So x is the number of days, and if you just type it in your pocket calculator, you can find that it means you have a factor 10 in growth after 10 days. Or you double the number of infections every 3 days. So yeah, it's really exponential growth, and it's for my opinion, it's growing quite fast. Okay, So we found out from our cases, so we are still below 10,000 cases. But what does it mean? If you look at this, is it true exponential growth for all times? So if you just put in like 100 days, then you will end up with 17 billion people infected by the coronavirus only in Germany. So it's very obvious that this cannot be true, since it's more than the world population. So it cannot be exponential growth for all times. But how can it be modeled then? Really simple approach. And this means, so that someone can get infected by the coronavirus, you need to have healthy people, and they have to get in contact with infected ones, and then you have corona infected. And the very simple model means you need someone with the coronavirus inside, you need a healthy person, and then after it you might get 2 infected persons. So to reduce the writing work, we just write corona with C, healthy with H, and yes, if you want to model something like this, then your reaction rate is the rate constant times the concentration of corona infected people and the concentration of healthy people. So this means when the virus starts, you have only very little concentration of infected people. This means your infection rate is quite low. And when you go to the end of the pandemic, then you will find that your healthy people, there are not so much left over. This means your reaction rate goes down again. Okay. So again, a simple model for the infection. This would be an infected person and a healthy person, and they form 2 infected persons. So I wrote here again the concentration as you know it from chemical reactions. So actually here it's not concentration, but it's number of cases. But I will stick to this concentration writing, since it's really familiar in chemical engineering. So, and this means the infection is quite similar to the autocatalytic reaction, this time only with 2 components. So you should know this from the last lectures, and yeah, this means you know how to model such a reaction already. And then we have a special situation. If one is infected, they will not stay with the virus, but they will become something, in literature I find it like closed cases, so CC, after let's say like 2 weeks. So this means that in the majority of the cases you are immune afterwards, so you will not get infected again, or unfortunately you could be dead. But I don't want to decide between this, I don't want to give prediction about that. I just want to say, okay, what will happen? Your number of closed cases is the number of corona infections 14 days earlier. So let's say if today is day 50, then you just go back 14 days. So 50 minus 14, this would be 36. Then you look at day 36, how many people were newly infected at that time, and this is just as a guess. This is your number of people that are closed cases right now. So number of corona infections will become closed case 14 days afterwards, and this can be modeled as a consecutive reaction. So what would your reaction system look like? You can write here the net reaction, that you just say, okay, I take a healthy person and the healthy person will become the infected one, and then as a consecutive reaction it will become a closed case. This infection, so the first reaction here, this you can model with the autocatalytic approach, and if you know your reaction rate, then you can say, okay, my number of healthy people, it will change by the reaction rate and the time interval. So for convenience reason it's useful to use 1 day here. Your number of corona infected persons is the rate that is given here, but you have to take into account that people will become closed cases, and this is just the number of newly infected ones 14 days earlier. Okay, and your number of closed cases, this will be your number of newly infected ones 14 days earlier, and then you just use the Euler scheme. You say, okay, if I want to have the value for my next day, so for my next time step, it's just the old value plus the change in healthy people, the change in infected people, or the change in closed cases. So this can be modeled. Oops. This can be modeled, and the first step is to get the reaction constant K here. And what I did is I just took the numbers from the Robert Koch Institute. This is the yellow line, and you can try to find a curve with. So you do your simulation and you play around with the reaction rate here, and then you try to match it as close as possible. And I did this here. So the blue line is the simulated value, and you can see that the comparison is quite good here. So you know the rate constant would be 3.33 times 10 to the power of -9. And then I put here the starting value. So I started with the simulation at day 14. There we had like 400 corona cases on day 14, and I just put here the concentration for the healthy people. I put just the inhabitants of Germany, so like 83 million persons. Okay, then now we've got this one here, and then the rest is quite clear. We know the starting values. So the starting values are 483 million inhabitants of Germany, and we have no closed cases at the start. So, and with this you can do a simulation that would look like this. So again, here you have the number of days, here you have the infected people, and then you can see that your number of healthy people is going down, and from this simulation nearly everyone is going to be infected. Here you can see the number of closed cases, and the blue line is the actually infected, is the number of actually infected people. So if you look at this, then you have only 1.4 million people will not get infected, so nearly all of the people might get infected. And you can also see that after 100 days nearly everything is done. So this could be the end of the pandemic, but the peak is really scary. You would have like 60 million people infected in a really short time. You can see this exponential growth here. Not very nice looking. Okay. Here I put a line for the 16th of March. So you can see we are here, and the infection numbers that we have, like 10,000, you will not see on this scale here. So it's like 0, and then you have this exponential growth. And I don't think that this is this is a real proper prediction of it, but at least there are some professional people out there doing the simulation, and they maybe came up with similar results, and you can see the effects in the other states. And that's why it was decided to have this lockdown on 13th of March. So we don't want to go into this scenario. This would be really, really catastrophic. So the lockdown was decided. What's the problem of the lockdown? You have an incubation period of approximately 2 weeks. So this means you have a strong time delay. This means that even if you stop all social contacts right now, a lot of people are still carrying the virus inside, and the number of infections will go up all the way. So if you look at Italy, I think Italy had the lockdown at like 10th or 12th of March. This is a logarithmic scale of the total cases, and you can see even though they have this lockdown, there's no really massive change in the trend here. So it's rather still an exponential growth, and yes, so this might take a time. I just said, okay, let it be like 2 weeks time delay. Okay, the other point is that the reaction rate, so your K, cannot be brought to 0. This would mean that you don't see other people for a really long time. So it would not be able to go to a hospital, you couldn't go shopping to buy food, or I don't know. There are still interhuman contacts, so you cannot bring it to 0. There will still be an infection rate. So let's assume that this new reaction rate goes down by 10%. It could be effective with a delay of 2 weeks. And let's assume a duration of the lockdown of 4 weeks. Okay, what would be the results right now? So these plots look a little, not very easy, let's say. Okay, so here again it's days, here it's cases, and blue line is the simulation of the infected ones. So what you can see here, we have this exponential growth, and even though we are closing it down, there will be no effect. The effect will only be visible after this 14 days that I put for the incubation time. So lockdown plus 14 would be a point in time where you could see an effect of it. And then we have here the yellow line. The yellow line are the closed cases. So this means, or you can see here, people are getting sick, but after 2 weeks they are becoming a closed case. So that's why we have this trend here. And then in this region your reaction rate goes down, because we have this limited reaction, this rate constant, and this means there are more people becoming a closed case than getting newly infected. So that's why we have this number of corona infections going down, and then due to this effect of this new rate, you have here again another turn in your curve. So then afterwards your number of infection will go down, but they will not go down very rapidly. So this will not hold on, but it will decrease really, really slowly. So, and here I said, okay, let's have a lockdown of 4 weeks. So this would mean, okay, this will be the end of your lockdown, and then I assumed, okay, let's have the rate constant as we had it prior to lockdown. So we had this 4 weeks lockdown, and then afterwards it's allowed to play football again, you're allowed to go to restaurants, to hotels, to travel, and so on. And then you would see that you have this strong increase here again. The exponential growth would immediately start again, and then your reaction rate would go up like this. So if you just say, okay, let's keep this for 4 weeks, and then you will only have a very limited effect, so not very good looking. Okay, then let's say we take this we take the social distancing very earnest, and we can limit the reaction rate to 5% of the initial value, and we will have a lockdown of 12 weeks, so rather a long period. What would your simulation look like? So you go down here, and then your cases are decreasing, everything looks fine. You nearly have no new infections anymore, but it's not going down to zero. You still have like a constant level of around, I don't know, 600 or 1000 people. They will stay infected, so some people get infected, some people become a closed case. So, but this would just be like a low level. But if you then say, okay, let's end this lockdown, everything looks fine, then again you will have this sharp increase here after the end of lockdown. So then if you look at China, so China is, if you just look at the newly infected people, you will see that they are over the top. Here you can see a plot of the active cases. So this jump here, this is something with the data, how they counted the people, so don't worry about that. But what you can see here in China, even though they have right now really limited numbers of new infection, about like less than 100 a day, you still see that they are not at zero, but they are about, I think it's something like 8,000 or so. And yeah, it will be interesting to see how things will develop. So then what I find interesting here is if you look at the graph a little bit more closely, then you can find that you have something like this slope, and then a change like this slope. And at least I think in my simulations here you can see that you have here like a steep slope, and then you have like a not so steep slope of your gradient of your lines. So this is not the same scaling and so on, and but I think that you can also find something that's inside the simulation. You can also find here in these figures from China. Okay, so I'm not a physician, but what I just from a chemical reaction engineering point of view, I would say, okay, what can you do? You can always switch between lockdown and normal life. So this means you would have something like infections going up, then you have the lockdown, infections going down, then you have normal life, infections going up, and so on, that you always behave like this. So I don't know if it's 4 weeks and 4 weeks, or if it's 4 weeks and 2 weeks, so but for me this doesn't look very attractive. Another things could be new rules of social behavior. This means even if you say, okay, after this lockdown you might change your life a little bit, so not interacting with people too much. I think big events are hard for the next time. So for me it's hard to imagine football matches with more than 70,000 people in a stadium. I don't know if we will see this in the near future. Maybe we can increase the hygienic standards, and maybe it's say, okay, maybe we can reduce the infection rate by 50%. I will show you some slides about it. And the best thing is to develop vaccines. I just had to look up the word Impfstoff, so vaccines. So with this you could just prevent the new infections. I think this is of course the best option, but it's very time consuming. So it's not like that you can say, okay, let's give us a fortnight, and in 2 weeks then we will have the the vaccines, I think this will take rather a long time before some new medicine can be given to people. So then let's not have a look at the detailed view, but if you say, okay, what will happen if we just have this 4-week shutdown and the rate constant afterwards will not be reduced? So here around should be the data that we just looked into for the shutdown and so on, and you can see like nothing here because the cases here are so limited. If we just say, okay, afterwards the rate constant is not reduced, then we will have nearly no gain of it. You can compare it with slide 12, so it's again like 60 million infections, and you only have like a delay of 4 weeks. So I think this will not be sufficient for vaccines. So from my point, or from this simulations here that might be totally wrong, I would say it's not enough to just have 4 weeks of lockdown and then everything will be fine. Okay. Then if you say you reduce your rate constant by 50%, so your k is not 3.33 times 10 to the power of -9, but it's half of it, then you would have something like this. So it's the peak is going down and it's moving to the right, so we have more time and we get less infections. And what you can also see here is that not all people will get infected. So here about like 20 million people will not get infected at all, but the peak is still 22 million infected, and we nearly have a delay of 100 days. So I'm not an expert in our medical system, but I would say that this is still much too high for a first-class treatment of every patient. So this is also not very good. So if we can bring it down to 1/3, then your curves would look like this. Your peak would be in a range of 4 millions, and you gain more time. So here you had like 200 days. So compared to the other slides, if you compare it to this or this, then you can say, okay, 4 million, this looks much better. We only have roughly half of the people infected with the virus. So is this enough? If you look here, your peak is like 4 million people. If you say, okay, of this 4 million people, approximately 5% will need intensive care, then this would be like 200 people at a time that will need intensive care. So again, not very promising. Okay, let me stress out again that this is not a proper medical simulation, but what I just did is to say, okay, let's assume the coronavirus behaves like a simple chemical reaction, and there might be some, they might act similar, and I'm just playing around with very simple equations. A lot of effects I neglected here. You have the effect of unrecorded cases, so maybe much more people are already infected. So maybe it's not 10,000 people nowadays that are infected, but maybe it's already 100,000 people infected. So this would be better for this simulation. Didn't put the temperature effects in it, so winter, summer, so summer should be good for a limiting of the pandemic. Here for the reactions you assume perfectly mixed people, so this is not the case, and I just said, okay, with this social distancing, I'm just reducing the rate constant, but so people will not be perfectly mixed. Maybe there will be a modification of the coronavirus. We don't know what this means. And I didn't do a proper literature review on pandemic simulations. I'm just simulating chemical reactions here because I know how this is done. But nevertheless, so maybe some effects might be captured by this approach, and when I thought about this course, I found, oh, this would be interesting to see how you can use chemical reaction engineering just for the coronavirus. So to make sure that you are not getting bored with live, here's some homework. You try to modify the MATLAB code that you had in the previous lecture. So there we had an autocatalytic reaction. You have to modify this. So now it's an autocatalytic reaction with only 2 components. And then we have the consecutive reaction for the closed cases. I just wrote you here how you can do it in MATLAB. Again, you need like a for loop. And inside this for loop, if I is your loop variable, then you can say, okay, this change in closed cases is just the change in infection 14 days earlier. So your I here, your counting variable should be identical with the number of days that you have. So for the rate, for the reaction rate, you can use the rate constant of 3.3 times 10 to the power of -9 for the normal infections prior to lockdown. So units are neglected here. And then you can also implement the rate, the change in the rate constant k with certain times. For example, say, okay, at day 40, I want my reaction rate to go down to 10% of its initial value, and then after 4 weeks I want it to increase again to the first rate, to the start rate, to the initial rate, or I want to stay it at, I don't know, half of the value of it or whatever. So basically this means implement it and play around with it, that you might end up with a similar graph that I did here. If you want to rescale your x-axis, let's say, okay, maybe you want to zoom in, then you can do this in MATLAB with just adding this line of code here. Okay, and in the next video I will give you like a little tutorial on how this is done. So then you can compare your homework if you did it correctly or not. Okay. Thanks for watching, and don't get infected. Bye.